In this video, we're going to introduce a new operation that we can perform on three-dimensional vector fields. Before we begin, I want to talk about the symbol that we use for the gradient of f. This upside-down triangle is called the del operator, or the vector differential operator, and can be thought of as a vector with components partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. When we apply this del operator to a real valued function f, we can think of it like we're doing scalar multiplication of the del operator by the scalar f. When a scalar is multiplied to a vector, that scalar distributes to each component of the vector. So that's why gradient of f is the partial derivative with respect to x times f, partial derivative with respect to y times f, and then partial derivative with respect to z times f. Now, it doesn't really make sense to take a partial derivative times a function, so what we're actually doing is we're applying the partial derivatives to the function f rather than multiplying. Now, since we're thinking about this del operator as a vector, we can do other vector operations with it. For example, we can take the cross product of it with another vector, or take the dot product of it with another vector. In this video, we'll take a look at what it means to take the cross product between the del operator and a vector field f. We define the curl of the vector field f with components f1, f2, f3 to be the following vector field. The curl of f is equal to the del operator cross f. To compute this cross product, we calculate the determinant of ijk, partial with respect to x, partial with respect to y, partial with respect to z, and then f1, f2, f3. So in the first component, we have partial derivative of f3 with respect to y minus partial derivative of f2 with respect to z. In the second component, we have partial derivative of f1 with respect to z minus partial derivative of f3 with respect to x. And in the last component, we have partial derivative of f2 with respect to x minus partial derivative of f1 with respect to y. Let's look at an example. So in this example, f is the vector field x times y times z, x squared plus z squared, and x times e to the yz. We're asked to find the curl of f. So again, the curl of f is the del operator cross f. So I want to calculate the determinant of the matrix where I have I, j, k on top, partial with respect to x, partial with respect to y, partial with respect to z, and then f1, which in this case is x times y times z, f2 is x squared plus z squared, and f3 is x e to the yz. So in this determinant, the first component is partial derivative of x e to the yz with respect to y minus partial derivative of x squared plus z squared with respect to z. The second component is the partial derivative of xyz with respect to z minus the partial derivative of x e to the yz with respect to x. And the last component is partial derivative of x squared plus z squared with respect to x minus partial derivative of xyz with respect to y. So this gives us xz times e to the yz minus 2z. Then we have x times y minus e to the yz. And then lastly, 2x minus xz. So that's the curl of the vector field f. One remark I want to make is that we can only take the curl of three-dimensional vector fields because the cross product is only defined for three-dimensional vectors. If I have a vector field that only has an x and y component, then we'll assume that the z component is 0. Let's now look at what the curl of a vector field tells us. The curl of a vector field measures rotation in some sense. At any point a, b, c in space, the curl of f at a, b, c is a vector that indicates rotation. The direction of the curl indicates the axis of rotation, defined by the right-hand rule, and the magnitude of the curl indicates the strength of the rotation. One way you can visualize this is by thinking of the vector field as some body of water, and the vector field indicates the current in the water. Now, at the point A, B, C, you can place a ball. That current might rotate that ball. If it does, the curl is going to tell you what the axis of rotation is, and also how strong the rotation is. Now, the larger the magnitude of the curl, the more quickly that ball is going to be rotated by the current. And finally, if the magnitude is 0, that means that the ball is not rotating at all. Let's look at some examples. In this example, we have f, the vector field x, y, 0, and we're asked to find the curl of f. Let's start by looking at a picture of the vector field f on the xy plane. Now let's imagine that I have a ball at any point on the xy plane. What does the vector field do to that ball? Since the vectors all radiate out from the origin, the ball will just get pushed further away. It will not spin at all. So I expect the curl of f to be the 0 vector for any point on the xy plane because there's no rotation at all. Let's confirm this by actually calculating the curl. The curl of f is the del operator across the vector field f. So that's the determinant of I, j, k, partial derivative of x, partial derivative of y, partial derivative of z. Then I have x, y, and 0. The first component is the partial derivative of 0 with respect to y minus the partial derivative of y with respect to z. The second component is partial derivative of x with respect to z minus the partial derivative of 0 with respect to x. And the last component is the partial derivative of y with respect to x minus the partial derivative of x with respect to y. Notice that each of these partial derivatives is 0. So the curl of f is the 0 vector, which is what we expected because no matter where we place the ball on the xy plane, the ball is not going to rotate at all. It's just going to be pushed outwards from the origin. Let's look at one more example. This time, f is the vector field minus y, x, 0. And I want to find the curl of f. Again, let's start by looking at a picture of this vector field. Now, if I place a ball anywhere on the xy plane, it's going to be rotated counterclockwise by this vector field. This is because as we move out, the current gets faster and faster. Since the side of the ball that's closest to the origin moves slower than the side of the ball that's far away from the origin, the ball is going to rotate. So I should expect that the curl is non-zero. If I go by the right-hand rule and the ball is rotating counterclockwise, then the axis of rotation is straight out the screen and it should point towards you. So let's calculate the curl of this vector field. We have that the curl of f is equal to the del operator cross f. So again, that's the determinant of I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, and in the last row we have minus y, x, and 0. So in the first component, I have the partial derivative of 0 with respect to y minus the partial derivative of x with respect to z. In my second component, I have the partial derivative of minus y with respect to z minus partial derivative of 0 with respect to x. And then in my last component, I have the partial derivative of x with respect to x minus the partial derivative of negative y with respect to y. So in the first two components there, all of the partial derivatives are 0, so I have 0 for the first component, 0 for the second component. In the last component, partial derivative of x with respect to x is 1, minus partial derivative of negative y with respect to y, that's negative 1, so 1 minus negative 1 gives me 2. So the curl of f is 0, 0, 2. So as we expected, the axis of rotation is in the z direction, and it points towards us. So that's where I'll stop for this video. In the next video, we'll find out more about curls and conservative vector fields.